Hi YouTubers, Dave out in Western Pennsylvania, USA. A continuation of our research with graphitic materials, commercially available graphite felt and graphite twine, sometimes called yarn. We're interested in the properties of the graphitic materials for use as electrodes in supercapacitor prototypes we are investigating here at school. And we really want to know more about the properties and performance of the graphitic materials with selected deep-eutectic solvents and lithium tetrafluoroborate electrolyte, which is a well-known standard in supercap research. We have here, and in prior videos I outlined this, we have these conveniently available plastic containers suitable for sections of a planar graphitic felt. And I have it soldered, the leads. I have a chromatography paper above and below the graphite, which you really can't see in there. And I have taken the leads and soldered them to a cotter pin. Just ease of hookup to put it into circuit with a commercial supercap, which you can see in back of it. Green cap supercap. I've had great luck with these commercially available supercaps. 2.7 volts, 100 farads. Pretty good capacitance. Now, in the industry, 2.7 volts is basically considered a safe upper potential for the supercaps that presumably have organic solvents like dimethylformamide, methyl carbonate, etc. We are interested in DESs. For example, a simple one would be, well, let me show you. Here's a sample of choline chloride with urea. I've been working with these for a number of years. It's a very simple one to make, rather inexpensive. Of course, there are ionic liquids closely related but not identical to DESs. And we also have some with the lithium electrolyte in the DES. Anyway, going back to what I'm showing you here, I have this planar plastic container. Incidentally, this will not react with dimethylformamide, this plastic. So if you use DMF in testing supercaps, make sure your container, of course, will not react with such a solvent. It goes without saying the container here does not react with the choline chloride urea solvent. 2 pieces of chromatography paper, one above and one below the graphite. And as I said, I have it soldered to a cotter pin, so it's in the circuit with the supercap. So what we're doing right now over here, incidentally, the history of the graphite felt, we did not clean it. Normally we do with isopropyl alcohol. We will be doing that in the near future. I want to see the performance of this graphite. I've measured the dimensions of it. I'll upload it. And we used it straight from the vendor at Amazon. And we did no cleaning of it. We did a prior run having this set up inserted in with a lithium-ion battery, and we ran 75 cycles up to 3.7 volts. See, our purpose here is to investigate raising the potentials of the supercaps from 2.7 with organic solvents up to, let's say, 3.7. So that's why I had it interfaced and in circuit with a lithium-ion battery. I have an upload on that. This is not a dry circuit. This is what I define as a wet circuit. Now, electrical engineers and electronic engineers don't define classically dry and wet circuits the way I am in these experiments. A dry circuit means the graphite has not been treated with any solvent whatsoever. It's dry. If it's been cleaned with isopropyl alcohol, we dry it to constant mass, and I would report that. This one was not. We are running here a wet circuit with graphite. In other words, it's been treated with a solution of the DES and lithium tetrafluoroborate, borate. And we have it running now with the supercap. And here we've taken some precautions to close the system. In future runs, I'll put a little bit of coating around the leads coming out. And we did some prior work here to make sure it was vented, but I don't expect the ionic liquid to evaporate. That's one of the advantages of it, very high boiling. Nonetheless, safety purposes with undergrads working with me. So we're running this right now. It had been run 75 cycles with a lithium battery up around 3.7 volts. I'll put the data. Interestingly enough, I'm looking at some of my notes here as we do experiments. There were some spurious results with the lithium run. Cycles 3 through 11 were aberrant, almost as if perhaps something was oxidizing on the surface of the graphite felt. Quite possible, it wasn't cleaned. Small details like this are very important. But then it stabilized, and it went from the starting capacity and energy output, the cycles returned to normal, and I'll have that data available. But something was going on from 3 to 11. But the mass change was only 11 milligrams before and after the 75 cycle run. Interesting. Well, anyway, we now have a wet graphite run. And here I'm using my ZKE Tech E-load device, which I like very much. If you buy one of these, let's say at Amazon or eBay, make sure you get EBC-A10H. That allows you to do cycles, which we're doing right now. If you get model A20H, it will only do single tests. So please make a note of it. And then you can download the software, EB Tester. I hope you can see that in the upper left of the desktop, EB Tester. Well, anyway, we have a number of these set up in the lab for students to use. Very good for home researchers, and many, of course, use this E-load device. So I'm running right now a 25 cycle run, bringing it up to 2.7 volts. And then the cutoff with discharge is 0.3 volts. And I'm using 600 milliamps for charge discharge. 1 minute rest time. We're up to cycle, let's see. I'm up to cycle 4. And so far, it's discharging, but so far so good, pretty consistent. After this 25 cycle run, if it's okay, everything's all right, I will then take it down to the other lab and I will run 100 cycles with the graphite sample in series with a lithium ion battery, so I can go up to 3.7 volts and see how it performs as a wet circuit. I'll be uploading data as I collect it, and I want to thank you very much for watching some of these videos, and we'll keep you posted on the results. Bye for now.